Hello, it's Dr. Daystorms again, and right now we're going to continue in Chapter 4, and I want to discuss, in particular, precipitation reactions and how to write molecular and net ionic equations. You've been doing it so far, but you haven't realized specifically that what we've been writing when we would make balanced equations was a molecular equation. First off, I want to explain and continue on the topic that we last left off with, which was the idea of precipitation reaction. So you can have two aqueous solutions, but when you mix them together, you get a product that is insoluble. And the last video, we discussed those that were the insoluble ionic compounds. And so when you react these together, you get what's called a precipitate that forms. This is a precipitation reaction. So I found this video on the web, and I thought that it's interesting. Plus, I like the fact that it shows you some of the pretty colored compounds that you can create from these precipitation reactions. And it gives you the chemical formulas as it goes along. Okay, so now we're going to talk about exchange reactions, which is really the type of precipitation reactions that we were doing. These are also called metathesis reactions, which unfortunately I don't believe the current edition of your book uses the term metathesis, which comes from the Greek that means to transpose. And so what happens is you can take two aqueous chemicals, two aqueous solutions, in this example, silver nitrate and potassium chloride. These are both soluble in water. And then when you mix them together, they swap their partners, sort of like swingers, if that helps you to remember what's going on. And whenever they swap partners, one of the resulting products is no longer soluble and it precipitates out. So in this example here, we would have, if you notice, we have silver nitrate and potassium chloride, and these are both water soluble. That's what that AQ means. It means that they're aqueous. They're soluble in water. However, whenever they swap partners, the silver, the cation from the silver, and the anion chloride come together, and it's insoluble. It makes that white solid. And then we have potassium nitrate, and potassium nitrate is still aqueous. And so what precipitates out is silver chloride. So this is called solution chemistry, and you have to really pay attention to exactly what species are present in that reaction. So is it a solid, a liquid, a gas, or is it an aqueous solution? If you're going to really understand the reactivity, you have to be aware of what is changing, and it's going to be the cation from one compound that mixes with the anion of the other. They're swapping partners. So let's go back to our example here. This is called the molecular equation. So what we've been doing so far when we were balancing our equations, where we were writing molecular equations. So we have silver nitrate in the aqueous form plus potassium chloride in the aqueous form, and then they swap partners, and so we get silver chloride, which now is a solid. That's the important thing. And then and then potassium nitrate. Potassium nitrate, which is aqueous. So if you notice here, we have things that were all in solution, but we make one solid product, and then we have the potassium nitrate, which is in solution. That, once again, is a molecular equation, but it doesn't really explain, or I should say, it's not necessarily the best reflection of what's going on. So we can write what's called the ionic equation. And in the ionic equation, anything that's a strong electrolyte, so we're talking about our strong acids, our strong bases, and our soluble ionic salts, dissociate into their ions. So, in this example, we now have silver, which was aqueous, nitrate, which is aqueous, potassium, which is aqueous, and chloride, which is aqueous. You have your chemical reaction symbol, the arrow. It makes silver chloride. Notice you cannot split that up because it's now a solid. But we still have potassium aqueous and nitrate that's aqueous. That really more accurately reflects what's going on in the species and what we can find. Okay? So now if we look at this again, notice we have a nitrate on one side of the reactants, and we still have a nitrate aqueous that's a product. So nothing really happens to the nitrate. Likewise, we have potassium aqueous, potassium aqueous. It's on both sides of the arrow. It's just like in math, when you have something that's on both sides of the equal sign. They cancel each other out. So, reality, what we really have going on is Ag plus aqueous plus a chloride anion, which is aqueous, that goes to make a solid silver chloride product. That's called the net ionic equation. So this is a net ionic equation. What you do, once again, is you cross out anything that does not change from the left side of the equation to the right side of the equation. Only thing that's left in the equation are those that changed. So in this example, we have the silver aqueous cation plus the chloride anion that's aqueous that makes the silver chloride. Everything else that didn't change are called spectator ions because they're just watching the chemistry happen. They are spectators. And so if I ask you a question, like list the spectator ions, it would be potassium and nitrate in this example. But they aren't important to the actual chemistry per se. So let's go through the rules on how to write a net ionic equation. First, you want to write a balanced molecular equation. Next, you want to dissociate all strong electrolytes. Third, you cross out anything that remains unchanged from the left side, the reactant side of the equation, to the right side or the product side of the equation. Rewrite the things that remain, and you have the net ionic equation. So, let's do an example. In this example, let's say that we have calcium chloride, and we want to react it with sodium carbonate. So you first have to figure out calcium chloride, and it's an aqueous solution. Since calcium has a 2+ charge, it takes 2 of the chloride anions. Make sure you don't forget how to do that. Plus sodium carbonate. Now, sodium has a +1 charge, but carbonate has a 2-, so it takes 2 sodiums for for 1 carbonate. And it too is aqueous. I'm going to do my reaction symbol down here just because I'm running out of room. Now we have to determine what's swapping partners, so to speak. We have a calcium cation with a carbonate. So let's rewrite that. Calcium has a 2+ charge. Carbonate has a 2- charge. And when you look it up on the table, it's going to be a solid. Plus sodium chloride. Sodium chloride is definitely aqueous. Now we have to balance the equation. And since we have 1 calcium, 2 chlorides, but we only have 1 chloride, we need to put a 2 in front of that. And lo and behold, we now have 2 sodiums, 1 carbonate, 1 carbonate. So that's our balanced molecular equation. Now, well, I'll change colors. We need to separate everything out that will break apart in solution. Anything that's aqueous will break apart. So we have a calcium 2+ plus 2 chloride anions. Both of these are aqueous. Plus 2 sodium cations that are aqueous. Plus a carbonate anion that's aqueous. It makes calcium carbonate, which is a solid, so we can't break it apart, plus 2 sodium cations, which are aqueous. Plus 2 chloride anions, which are aqueous. Now, let's look at things that did not change. If we look at the calcium on one side and the calcium on the other side, they did change. It went from aqueous to a solid. Same thing with the carbonate. So those we cannot break apart or can't get rid of. However, if we look here, we have 2 chlorides that are aqueous. We can get rid of them. And we have 2 sodium aqueous and 2 sodium aqueous. We can get rid of them. So let's just write what's left behind. We have a calcium 2+ aqueous cation plus a carbonate 2- anion that makes a calcium carbonate solid. Now, if I asked you to say what were the spectator ions in this example would be sodium and chloride. So this here is our balanced net ionic equation. Calcium 2+ aqueous plus carbonate 2- aqueous makes calcium carbonate solid. Hopefully, this will help you answer these types of questions, and I suggest that you do as many examples and suggested problems as possible, so that way it becomes second nature to you. I'll see you in class.